So, welcome everybody to this webinar on monitoring of active distribution networks. I am Rajarshi. I did my PhD from IIT Kanpur in the year 2022. I defended in March. Uh, Before that, I had a BTech degree in electrical engineering from National Institute of Technology, Silchar, and I had a master's also in power system engineering. Currently, after my PhD, I'm working as a senior engineer with MathWorks, where I am mostly looking on modeling of renewable energy sources to distribution and transmission networks and their impact on the grid. So with this, I will start our today's presentation, which is on monitoring of active distribution network. And this is the work that I did during my PhD. So let's begin. Yeah, so the brief outline of the talk that I will be covering these four topics. I will discuss about active distribution networks, what are the challenges in such networks, monitoring of this kind of networks, modeling of the active distribution networks for performing system level studies, state estimator for active distribution networks, topology detection for active distribution system, and finally I will show some parameter estimation algorithms for active distribution systems. Yeah, so let's first define what is an active distribution network. So according to a SIGRE working group committee report, an active distribution network is a network which have a combination of distributed energy resources such as solar PV generators and other DERs, and also controllable loads and storage integrated to the system. The distribution system operator under such a scenario has the possibility of managing the electrical power flow in the network by using various schemes such as flexible network topology or using other devices such as STATCOMs and also. So they can change the power flow in the network to suit the voltage and voltage profile of the network. Now, the DERs in such system also can take some degree of responsibility. So DERs are the distributed energy resources such as PV or wind or a battery system. They can take some degree of responsibility for system support, such as voltage support for the system. So this report actually talks about being able to operate such networks both in a grid connected mode or in an islanded mode. But in this talk, we are mostly focused on the on the grid connected mode of operation. So what are the challenges in such a system? So this is the basically the difference between the conventionally passive distribution system and an active distribution system. So in the passive distribution system, the power flow was basically unidirectional, and as a result, the power flow was unidirectional. So we uh, so as a result, the voltage profile would be a flat profile, like it would be decreasing with the nodes we traverse far from the substation, the voltage gradually decreases. However, in an active system, there can be bidirectional flow of power, and as a result, the voltage profile can be different, quite different from what we have experienced previously. That is because of the backfeed. Now, because of the backfeed, at some point, if there is a more renewable generation, then the voltage profile at that point can be higher than other points in the network. So it's now not following such a linear trend. So and moreover, the renewable sources such as solar and wind, they show some intermittent variation in their output power, which will cause the bus voltages to dip and rise with the change in the power flow of those renewable sources. The network, which is basically the distribution network, are inherently unbalanced in most of the cases, and another problem with distribution system is that even for a small geographical area, if we consider such systems, they will have a lot of measuring nodes. They will have a lot of nodes in the system. Like nodes in the system are like, if we consider all the pad mounted transformers to be one node which we want to monitor. So even for a small geographical area, there will be a lot of such transformers, and as a result, there will be a lot of such nodes to be monitored. And we don't have enough measurement devices placed in the network so that we can monitor all the nodes through our measuring devices. So such networks are only partially observable using the available measuring devices. So such networks lacks the amount of measuring device. Now, if we look at a typical active distribution system in this working figure, so you can see that there can be measuring devices in the network such as RTUs or smart meters, and sometimes PMUs or micro PMUs, what they call. But these are really sparse, and most of the nodes or the buses in the network would be unmetered. So we don't have measurement for most of the nodes. Typically, the economical aspect, which is related to with measuring devices, which limits, typically the economics of the system limits the placement of measuring devices to every nodes. Yeah. Now, what is the DSO trying to achieve uh, in such system? So we can see whatever measurement is available in that system, that will be communicated to a database and also to the other functionalities such as a state estimator. So the state estimator receives the measurements which are available, and if those measurements are not enough, which is the case for distribution system, then the state estimator will also require to access the database or use some pseudo measurements generated from historical data. And the state estimator, uh, which is trying to estimate the state of the system, will also require the knowledge of the network model, which comes from the topology processor, and also the parameters of the line connected in the system. Once the estimator gets all this information, it will perform the task and will return the estimated states of the system. Using the estimated states, the DSO can take various control decisions such as voltage control or reactive power support, energy management, market operations can also be done. Most importantly, if any of the devices are giving some erroneous data, if that can be detected, which is a difficult thing to achieve in distribution system, if that can be detected, the state estimator would detect such bad measurements. And also it can with the estimated states, the DSO can perform security monitoring. It can see whether there is an overflow or overloading in the line, or or a voltage dip beyond the permissible limit in any of the nodes. So it can check those and can take required emergency or preventive controls. Now, to perform such system level studies in the distribution network, we first need to formulate how we model this system. So let's look how we will be, what modeling approach we are taking. So basically for this kind of studies, we are taking the time series modeling approach of active distribution networks. So we are only interested here in finding the algebraic states of the system, which are typically the bus voltage phasors, and therefore the most of the equations involved in such a modeling are algebraic equations. This kind of study using the time series modeling is uh, is uh, is applicable for the for observing the algebraic states mostly. The dynamic states such as the generators or converters, if there are any converter interface renewable sources, those internal variables of those generators and converters are not observable using this modeling scheme. And in this scheme, we consider that we are connected to a grid. As a result, our frequency is not varying. That is, we are connected to a strong grid. Variation in the bus voltages are observed in such a modeling. The main purpose of such modeling is to observe the variation in the bus voltages over a slower time scale, typically in seconds or in a few milliseconds, like hundreds of milliseconds, not less than that. So we are observing at a slower time scale. Now, how we typically do this kind of time series simulation? So let us explain it with a 123 bus feeder case, which is a IEEE feeder. So in this setup, we typically will do a three-phase power flow for the whole network. Okay, so the three-phase power flow will give us the voltages and angles. Uh, so in such cases, the substation of the network is the grid connection point, and it is acting as a stiff source like a slack bus. And the renewable power generation in these cases are considered to be grid following sources. Therefore, they are exchanging power at the grid voltage and frequency. The loads are modeled as constant power and constant impedance loads. Uh, so we need this network model, and we need typically the power profile of the renewable generations or the sources or the loads to find the bus voltages and angles using a three-phase power flow. And this is how this algorithm works, the three-phase power, the time series simulation using three-phase power flow. So we typically start with a power profile of the loads and renewable generation. We we consider that we know the network model and all the line impedances. We form the Y bus. We know the topology. We form the Y bus matrix, and we consider the substation, which that is the grid connection point, as the slack bus. And for that bus, we consider the voltage magnitudes to be at the prescribed level and the angles to be the reference angle for a three-phase system. And then we initialize our three-phase power flow using a flat start. We do this in the rectangular coordinates. This can be done also in the polar coordinates. So we convert all the power injection to currents, and then we do this kind of three-phase admittance matrix-based power flow. And once it converges, we have got the voltages for that particular instant. And once we get that voltage, we check whether we have converged. If we converge, then the next job is to go for the next time step. So we increment the time step, and then we again do the same thing with the load data and the network data for the next time step. And in this way, we simulate a time series power flow. So this is a simulated result which we are showing. So we are varying the loads and generation in the system with the time, and as a result, our voltage magnitude and voltage angle. Here I am showing for phase A. These are also for phase B and C. So they also start varying with the variation in the power flow of power injection of the renewable sources and loads. Now so we have defined the base case, like how we model such network and how we perform a time series simulation on them. Next, we are looking for state estimator to perform state estimation in active distribution system. So state estimation in power systems is basically, what is the task of a state estimator is that it will estimate the electrical state of the network, which is the state vector in an electrical power system is typically the bus voltage phasors. And so it estimates those bus voltage phasors in the presence of inaccuracies and errors in measurement data and network model. So the measurement data are never 100% accurate. The measurement have some inaccuracies associated with them, and there can be some inaccuracies in the network model itself due to some missing circuit breaker status or incorrect circuit breaker status. So considering both these inaccuracies, how can we estimate an optimal state of the system? So this is the process of state estimation. So if we define it in a mathematical way, then the state estimator will take inputs as the measurements from the system, the network data such as line parameter data and the topology data, and some prior belief will be taken into the estimation, into the statistical estimation. What are this prior belief can relate to the nature of the noise distribution for the measurement. It can also relate to a pseudo measurement which we have generated using historical data. So that is also a prior belief. So those also gets integrated into the system. So what it does is that we have some prior belief about the current state. Here X is the state vector of the system. So we may have some prior belief about the current state of the system, and we also get some evidence about that from the measurements. So this evidence is the current measurements that we are getting. Using the measurement, we will have some estimate of the state, and combining these two, we will get a posterior estimate of the states. And the state estimator typically tries to maximize this uh, a posteriori probability of the observing the states given the measurement and the prior belief. So we have a set of prior beliefs, we have a set of measurements, we combine them, we form the posteriori distribution, and we find the state such that we find the state such that the posteriori is maximized. So the estimated states are those states which maximizes the joint probability distribution of the posteriori, which includes the prior beliefs and the measurements. So as you can see from this setup, if we lack in measurements, then the estimation will not be accurate. However, if we have a very strong if we have a very strong prior belief, which is we gather enough information from prior data, then we can compensate for the lack in measurements. So this is what typically a distribution state estimator will try to achieve. It will try to compensate for the lack in measuring devices which are not there in the distribution system, using some prior belief about the evolution of the system states. Otherwise, we are always at an unobservable scenario for a distribution network. So the prior belief plays a key role in estimating the states of a distribution system. Uh, Next, the state estimation in power networks. So the bus voltage phasors are the algebraic states of the system, which are needed to be monitored by the DSO to take various control and restorative actions. So this is a conventional state estimation framework for power networks. So this is a network. It has measuring devices such as RTUs, PMUs at some of the nodes in the system. The estimator here we are talking about is the conventional weighted least square estimator. So what it does is it gathers the measurement data, and and we formulate measurement functions. Like we express this measured data using the states and the topology of the network and the line parameters. So this H is a measurement function which expresses the state vectors such that they are related to the measurements. So the measurements can be expressed as a function of the state vector using this measurement function H. And since there are inaccuracies in the measurements, so epsilon is the measurement noise which captures the inaccuracies in our observed measurements. So this epsilon is typically considered to be from a Gaussian distribution. We can get that information about epsilon from the measuring device. The device manufacturer basically specifies how much the noise can be there in the measurements from those devices. So from there we can get the statistics about this measurement noise. And R is the covariance matrix of the measurement noise, which is assumed to be Gaussian distributed. Now, with this assumption of Gaussian distribution on the measurement noise, we can formulate this weighted least square. So if we minimize this function such that and find the states by minimizing this function, we can find we obtain the optimal states of the system through this weighted least square estimator. Now, in a distribution system, as we can see, when we are having a lot of renewable sources connected, there can be sudden spikes in the power flow of in the power injected by those sources to the network. So this is a measurement snapshot taken from RTU connected at IIT Kanpur substation, and we can see sometimes the power profile are showing some spikes. This could be because of the renewable generator is showing those spikes. And now need for so there is a need to observe those variation caused in the states due to the variation in such power injected by the renewable sources or a sudden change in the load. So we need to observe the states when such a scenario is happening. So for that we need this kind of an estimator which we call the tracking estimator. So what it does is that it will try to capture the variation in the state during these intermittent changes. So the problem with this sudden intermittent changes is that since most of the nodes in the network are not metered, so we may not get the information about this sudden change in power. We may not have a measuring device at this node itself where the power is fluctuating, and as a result, we are not able to observe this fluctuation, and our prior belief cannot like accurately tell us when this power is going to fluctuate. So the pseudo measurement that we may generate for such unobservable nodes using historical data may fail to capture this sudden variation. So conventional state estimation methods for distribution networks which relies on the pseudo measurement generation may fail to track the variation in the state when a sudden change in the power is happening. So this is the typical setup of a tracking estimator. Now, in a tracking estimator, we have a predictions for the states. So we have a prediction model for the states. This typically is done using historical data. So this is kind of a prior belief about the evolution of the state. And using that predicted state and the measurement available at that instant, we do a correction on the predicted states. And this is typically done using a Kalman filter framework. Here K is the Kalman filter gain. So using this Kalman filter framework, we correct the predicted states and we say this is our best estimated states for that instant. And then we again go ahead with the next time step and do the same thing. Now, the H here is the measurement matrix. It is typically linearization of the uh, nonlinear function H at that point. And P is the uh, uncertainty associated with the Gaussian noise in prediction. So the prediction step will also have some uncertainties, and that uncertainty is captured using this epsilon, and P is the covariance matrix for that uncertain noise. Now, as we have already discussed, that the sudden variation cannot be captured using the conventional model which we just show, that is using the conventional Kalman filter based tracking estimator. We cannot observe the sudden variation in the state. This is typically because the prediction cannot model the sudden variations. So the predictions cannot model the sudden variation. As a result, what we propose is that we say, okay, we keep this part of the state vector, which is the steady state variation, and we call this as x s of k. So this is the steady state variation part of the state vector, uh, and that can be predicted using the using the forecasting model which we just showed. So the prediction model can be correct when the system is evolving slowly. However, when there is a sudden change, we say we have an additional component to the state vector, which we call the augmented part of the state vector, and we call this as xv. And this denotes the part of the state vector which only becomes active when there is a sudden variation. And as you can see, the steady state part will follow the prediction model because it is under slow variations. However, this xv is occurring due to a sudden variation, and it cannot be captured through this prediction model. So how do we capture xv? So this is the question that we are asking here. So one assumption that we are taking as a prior belief for this kind of model is that we are not considering about a major contingency like a blackout. So we are considering only sudden variation at few of the nodes in the system. Okay, so we are considering that the sudden power variation, sudden large power fluctuation at any instant can only happen at few of the nodes in the system. They cannot co-occur at more than 50% of the buses. So typically we are saying that the co-occurrence of sudden change in the system is limited to few of the buses, which is kind of a realistic assumption unless a major contingency is happening. So what this assumption leads us to is that if we look at the change in the injection of currents in the buses, if delta I represents the change in current injection at the buses from a previous timestamp to the new timestamp, so this change in the current vector will be a sparse vector. Why? Because we are considering that this change is only happening at a few of the buses. So delta I is the vector of change in injection for all the buses in the network. That's why we call it a 6n, because for each bus, if we consider there are three states, six states, then for n buses there will be 6n states. And now we augment the whole state estimation formulation to capture this xv. And how we do that is that our state vector was the sum of these two components. So if we just split this up, this is the conventional formula, conventional state estimator. And if we add this prediction part for the quasi steady state part, so this two part basically is like the conventional Kalman filter. However, what we add to this formulation is this lambda times of L1 regularization of B times of change in the sudden change part of the state vector. Okay, so what it does is that, and what is B? B is this matrix which is formed using the Y-bus element. So B is this matrix which converts the change in state vector into change in current injection, basically. So, and this lambda is a scalar which needs to be tuned. Okay, so what it does is that now this L1 regularization has a property uh, to uh, to enforce sparsity. So so what this L1 regularization of this thing does is that it will make this delta I to be a sparse vector. So now our objective function is looking for a state vector which satisfies the excess with the steady state part according to the Kalman filter formulation, and the sudden change part such that the sudden change only occurs at few of the nodes in the system. So it will try to fit the measurement and the prediction such that the steady state part fits the predicted model, and the sudden change part is reflected in such a way that the sudden change in current injections are happening at minimum number of buses. And if we do that and we solve this problem, so we come up with this kind of a formulation. So this is what we call the L1 norm regularized forecasting aided state estimator. So we have our prediction model. From that we get the predicted state for the quasi steady state part. And in step 2, what we do first, we uh, we solve for the sudden change part of the state vector by keeping the uh, steady state part as the predicted one, and we solve for the sudden change part, and then we update the steady state part using the recently estimated sudden change part and the predicted steady state part. So we update this steady state part, and then we tell that the total state vector in our case is sum of these two parts, and this is our state vector, and this then again goes to the prediction model. And in between we can also go and update the prediction model itself, because we have got an updated steady state part. So we can use a recursive formulation, a recursive reweighted least square formulation to update the prediction model itself. The A is the prediction matrix, which is also called the state transition matrix. So we keep on updating this matrix as we update the state vector. Now, the results for such an estimation is that we consider the IEEE 23 bus feeder. We place PMUs and RTUs in the system, and we also have renewable generators such as PV. You can see that for this system, we have the unobservable nodes marked using this circle, and the PMUs in these networks are placed such that we achieve minimum number of PMUs, and we achieve a criteria which is called the depth of one unobservability. This ensures that every unobservable node has its neighboring node as observable. So there are no two consecutive unobservable nodes in the system. So this placement criteria will ensure that, because what is the case that we are trying to achieve is that the information for the unobservable node, we are trying to gather it from its neighbor. So we want the neighbor to be at least observable, and so we do this using this depth of one unobservability placement criteria for PMUs. So this requires a far lesser number of PMU than making the full system observable, like it is half of that number. So, and these are the estimated states that we observe. So during like variation in the system, we observe that our predicted states and the estimated states, they are matching, like our simulated state, which is the base case, which is simulated using the time series load flow, and these are our estimated. This estimation is done considering noises in the measuring devices. And this is what happens when a sudden change is happening at the unobservable node. So an unobservable node is like this bus 50 is an unobservable node, and we do a change in this bus, a sudden load change in this bus, and we see that the conventional estimator is not able to predict the states correct very accurately. However, our formulation is leading to a close enough estimation of the states. So, and next, another part of the work that we do is around topology detection. So here we talk about topology detection in distribution systems. So what is the need for topology detection in active distribution network is that active distribution network, the system operator may change the network topology, or the topology may change because of faults, and for clearing a fault, doing some fault var optimization. And what is seen in many instances is that the SCADA system, it typically gathers the information about the change in the circuit breaker status. However, due to communication issues and data updation issues, sometimes the CB status are not correctly reflected in the SCADA system. This has been observed in various practical scenarios. So the SCADA system may not be able to log the right circuit breaker status. As a result, the topology of the network is not correctly estimated, and and all the processes that depends on this topology information, such as state estimation, will not give us good results if we don't have the right topological information of the network. Now, how do we address this issue of of uh, of a of a CV status being not correctly reflected in the SCADA system or incorrectly reflected? So we go for a data-driven method for topology detection. So what we assume in such scenario is that we have a network where the system state is varying in a quasi steady state fashion. So the state from uh, previous time step will change to the next time step steadily, and that variation is reflected using this. We don't have enough information about the variation, so we assume it to be a Gaussian distributed variation in the states, and that variations covariance of the state variation is represented using the sigma of x, and we gather measurement from the system, uh, and these measurements are again as a function of the state, and we represent them using h of x, and alpha is the uncertainty associated with the measurement. So one of the key observations that we are using to find the topology of the network is this. So it has been observed in various work that the inverse covariance matrix of bus voltage phasors. Okay, so the inverse covariance, if we collect the bus voltage phasors from all the buses in the system, if we were able to do so, and we form an inverse covariance matrix of those bus voltage phasors, then this inverse covariance matrix has information about the network topology. And what is this information? So typically the elements, the off diagonal elements in the inverse covariance matrix, if they are positive, okay, if they are positive, then there is a line connecting between bus I and bus J. Okay, and and if and sorry, if they are uh, if they are negative, then there is a line connecting between bus I and J. And if they are positive or zero, then there is no line connecting between bus I and J. So if we set a threshold such that if such that the off diagonal elements are always less than that negative number, so in that case we can say that yeah, this ij element is connected because it is a negative number. And how do we now estimate the inverse covariance matrix of the system? So this assumption is on the state variation, that is they are varying following a Gaussian distribution. So this delta x, that is the variation in the state, it follows a Gaussian distribution with covariance sigma x, and we are interested in finding the inverse of this sigma x. So we know that the delta x belongs to this Gaussian. So the Gaussian probability for this delta x will be given by this function, and we want to find the sigma x from this function. So to test the Gaussianity assumption, we collected some PMU. We connected a PMU at the IIT Kanpur network, and we collected measurements over a time period from this device, and we measured and we calculated the change in the measurement at every instant. And when we closely do a histogram plot of those change in phase angle measurements, we see that it is kind of roughly representing a Gaussian distribution. So the Gaussian assumption is kind of valid in such a scenario. So this model is being discussed in various existing methods where this exact formulation is used to estimate the inverse of the covariance matrix from this function. Now, this is the typical setup that existing methods used to find the inverse covariance matrix. So theta is typically the inverse of the covariance matrix, and S is the sample covariance matrix of the change in measurements. Okay, change in phase angle measurements in this case. So S is the sample covariance matrix over a collected snapshot of change in measurements, and we typically minimize this distribution function. And this L1 is a penalty on the estimated inverse covariance matrix, because we know most of the buses in the network, like all the this matrix is going to be a sparse, because the distribution networks are mostly not that densely connected, right? Any power network is not that densely connected, so theta is mostly a sparse. So we encourage sparsity using the L1 norm on the estimated inverse covariance matrix. So the basic premise of such setup, which is currently being used by various method, is that this sample covariance matrix S is can be reliably calculated from this collected snapshot of change in phase angle measurements. So the this, however, what is observed that this S is very close to its population covariance. Like we are collecting only a few samples, so this S becomes close to the ideal scenario when this this change in phase angle measurements are from a Gaussian. So if this change in phase angle measurements are from a Gaussian, then this calculation of this S will give us a reliable value. However, if these delta x are not from that, not from an accurate Gaussian, okay, so in such scenario, the calculation of S itself is erroneous, and we cannot expect to get the right inverse of it, that is theta, and the correct topology cannot be inferred. So what are the situation under which this assumption of Gaussianity on delta x may not hold? Is like this such scenarios where a sudden change in the power is happening, or a bad measurement happens in the PMU data. So under those scenario, the Gaussian assumption kind of is not accurate, and under this setup, this conventional database formulation may not work. So what we propose is that, so this is what will happen in a power variation. Here the variations are quite close enough, but suddenly a change happens and the Gaussian assumption may not hold for this sample. Okay, so what we see is that we want to penalize such variations. Okay, so if in our current formulation we can somehow tell the estimator to neglect those samples which reflects this sudden change, then we can do a decent job. So how to tell the estimator to 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 don't give importance to such variations for estimating this topology? So for that, we assume that the distribution itself is not Gaussian, and it's a heavy tail distribution. So our assumption on the distribution for probability distribution for delta x is some generalized distribution G, which is not a Gaussian distribution, and F is the density generator for that distribution. And we, instead of the sample covariance, we take the surrogate of a covariance matrix and we call it the scatter matrix gamma. So gamma is the scatter matrix of this generalized distribution on delta x, and this could be a heavy tail distribution, not a Gaussian. So if we do a maximum likelihood estimation to find the gamma for this system, we see that this gamma will come out to be this equation as represented in equation 13. And what we can observe from is that the gamma is both in the left hand side and right hand side. So this is an implicit equation, and we need to have an iterative method to solve it. So we typically use this iterative technique to solve for gamma, and we keep on iterating unless we converge. And u in this case is this function. Typically, when we do a maximization of the likelihood, we arrive at this kind of a u. And so what could be this u? Since we have not assumed anything about f yet, so we cannot tell anything about u. Okay, so we will see how can we arrive at a u which will do the job for us. And so we call this u as the weighting function, weight function. Why we call this u as the weight function, you can see is the reason because u of this whole variable is acting as a multiplier to this delta xk times delta xk, which was the way of calculating our sample covariance. So this u of this variable is acting as a weight for the elements of the sample covariance actually. So that's why we call this u function as the weighting function, weight function. So if we can suitably design this weighting function u, then we can give lower weightage to outliers and sudden variations. And as a result, we will give them the lower weightage, and we can get a decent enough sample covariance matrix which we can estimate and invert it to find the network topology. So the weight function in general should have these properties. It should be non-negative, continuous, and non-increasing. So it should decrease as we go far away from the assumed Gaussianity. So we take a function v of x, which is always positive because it's a positive definite function, and gamma is the scatter matrix, which is the symmetric matrix. So as a result, this function is always positive definite, and we take u as a function which is inverse of this function v. So this v, you can see v is a function which increases with increase in delta x. So if there is a sudden variation, delta x would increase, and this will lead to an increase in v. However, 1 by v will be less for such case, so we will deviate the sudden variations and bad measurements. So in this way, we can find u as inverse of this function v, and when delta x is very close to 0 or 0, we assign it to 1 to avoid discontinuity. So the topology estimator using this u can be formulated such that using this u function, we will calculate the gamma, and we will use the gamma instead of the calculated sample covariance matrix S to find the inverse of this gamma matrix, which we call the Chi matrix. So we call this as the inverse of the scatter matrix. Gamma is the scatter matrix, and we solve this one and we find this inverse scatter matrix to find the topology. So the typically the heart of it is estimating this scatter matrix gamma. So we start with a positive definite matrix assumption on gamma, and we typically in this case we started with a gamma of identity, and then we repeat this iteration unless we converge. So when we converge, we stop, we say that we have found the optimal gamma, then we put this gamma in this equation 19, that is this optimization, and we obtain the inverse of this gamma. And now the inverse of this gamma, elements of the inverse of this gamma gives us the information about the network topology. So we take the IEEE 37 bus system as the base case. We obtain measurements from few of the nodes in the system, which we place the PMUs in an optimal way, and we obtain the measurements from those PMU, and we see when we solve it using the inverse scatter, sparse inverse scatter matrix, we actually are able to obtain the true information about the network topology. However, if we use the conventional formulation, that is the inverse covariance matrix, so in the presence of bad measurements or sudden change in the power injections, this some erroneous identified edges are there in the network. So this matrix typically reflects the bus connectivity. So these are the bus number, and each off diagonal element shows which bus is connected to which. And here we see using the covariance matrix, we don't get the reliable answer. So the next final work that we talk about is a line parameter estimation method. So typically the setup that we consider is that we have measuring device now at both end of the line, because if we don't have that, we are not able to measure calculate the line parameters. So we have RTUs at both ends. In this case, we have CTPT, which are providing the measurement to the RTUs, and the RTU measurements are expressed as a function of the states and line parameters. So here this P is the line parameter vector, delta is the voltage phase angle, and U is the voltage magnitudes. So the voltage magnitudes are also obtained from the RTUs. Okay, so we can have a voltage magnitude measurement from the RTU, but these measurements, as they are usually associated with some noise, which is the measurement noise. So these voltage magnitude measurements are associated with noise, but we get them from the RTU. So we have the power flow measurements from the RTU, which we collect in this vector Z, and we express this power flow as a function of the voltage magnitude, line parameter P, and voltage angle delta. So we don't know angle delta and P, but we have a information about the voltage magnitude, and this information is erroneous. That is, this voltage magnitude is associated with the measurement noise. Therefore, this nonlinear function, in its input, it also has noisy elements, right? And we are trying to estimate the parameter and voltage angles, which we don't know. So how do we do that? So for that, what we do is that we express the noise in the input of the nonlinear function to the output. Okay, so that is the noise in the voltage magnitudes are converted to noise in power. That is the voltage magnitude noise, how they are reflected in the power. We do that through this effective variance. So typically this power is a nonlinear function of the voltage magnitude V, and if there is an uncertainty in V, if we linearize it, what kind of uncertainty we will get in P because of this uncertainty in V. This is reflected using sigma P. The sigma P is the kind of propagated noise in this case. And using this propagated noise, what we do is that we calculate the variance, which we call the effective variance. So this includes the variance of the power measurement itself and the propagated variance through the voltages. And we invert this net effective variance to obtain the weighting functions for our estimator. So the estimator that we are using is a least square estimator, weighted least square, and it has this weighting function W. So this weighting function becomes a function of the derivative of power with respect to voltages. Therefore, this derivative of power is itself dependent on the line parameters. Therefore, this weighting function is a function of the line parameters itself. So as a result, we arrive at a nonlinear least squares, and we solve it through an iteratively reweighted scheme. So we initialize with an assumption on the voltage, angle, and line parameters, and then we calculate the effective weight of the measurement, that is the power flow measurements. Then we solve the optimization problem with those calculated weights, and we obtain the updated parameters. Using the updated parameters, we again go ahead and update the voltage magnitude measurements, and then we check whether we have converged in terms of parameters and voltage angles. If we don't, we repeat it and we reweight it, and we reweight and then optimize, reweight and optimize until we converge. And this is the scheme we call as reweighted least squares. And the results that we obtain, like first we show some simulated results. So here we have a Simulink model, and this power profile for this model are taken from IIT Kanpur network data. And we do a Monte Carlo simulation used by varying the measurement noise in the RTU measurements for the simulated case. And this is a Monte Carlo trial over 1,000 simulations, and we see that most reliable we are getting the error in line parameters under the considerable band with the effective variance method. However, if we don't use effective variance, we use the conventional least square formulation, and we don't reweight the measurements. That is, we don't take into account the voltage uncertainty in the voltage magnitude, and then we get results which are inferior to what is achieved by reweighting. And then this is a case where we estimate the parameters of a cable connected in IIT Kanpur. Okay, so this is a 11 kV network cable which is connected in IIT Kanpur, and collecting real RTU measurements, we estimate the parameters of that cable. And we carry out this exercise also with PMU data. In this case, instead of taking the power flow, we take the line current flow measurements from the PMU as our Z vector, measurement vector, and we get both voltage and angle from the PMU. However, they are associated with noise, and we use the effective variance formulation. So we do this exercise for a utility in India, and we implement this algorithm through a Python-based web app, and we provide this web app to the utility. And this is the results for that utility line. 132 kV line of the utility, which had PMUs connected at both ends, and these are the results that they obtain for those systems. So thank you, and I'm open to take questions.
So excellent. Thank you very much for such informative presentation in which we really could learn a lot. The topic, all topics related to monitoring are today very close to real applications. You are using smart technology, you are using phasor measurement units, you're coping also with the topology estimation problem, which is quite an interesting one, because without proper topology, we cannot estimate the state. So that you're dealing with active distribution networks, which you have clearly defined. You showed us a number of aspects related to modeling, related to solving the problem in a classical standard way when it comes to state estimation. We're talking about lack of data in distribution networks and pseudo measurements. So such a huge, massive number of very interesting things. My apologies for background noise, but now I would like to inspire our attendees to ask a question. Please raise a question, and Wei, please just handle who will ask and so on. Please.
Yeah.
Okay, thanks, Professor. If anyone have any questions, please feel free to ask. You can raise your hand or you can just unmute yourself and ask the question. Thank you.
Hello, Rajashi, right?
Yeah.
Yes.
Yes.
Thank you very much for this amazing presentation. I really learned a lot from your presentation. And I have got a few questions. It's mainly about the measurement, because basically you use PMUs and RTUs, and as mentioned, your focus research is actually in distribution network, especially in active distribution network. So my concern is that actually in distribution network, we do not have that many PMUs, or even RTUs. The majority of the buses is actually measured by the smart meters. So, so what you can do if we do not have enough PMU, for example, the method proposed for topology detection. So, what can you do in these cases?
Yeah, great question. So yeah, as you can see that I have used PMUs for topology detection and state estimation. That's true. And what I have tried on those methods is that to reduce their numbers. Okay, so I use different method measurement placement techniques to reduce their number. So that aspect I focused. However, what I observe is that if we are interested in capturing the sudden variations in the states which are caused due to variation in renewable power or load change, so then we need a measurement with high refresh rate. Like if we don't have PMU, if we rely only on smart meters, we will miss. There is a very high probability that we will miss the window where this change is happening. So this is really, so this highlights the fact that we need to place those measurement in the system if as they are getting complicated, and if we are interested in observing the variations in the states, then we need to have high refresh rate measurements. Like with the smart meters, we can't really achieve to track the variation in the states or to track a sudden change. So yeah, but however, we have to focus on minimizing their numbers, and that's what I discuss at length in my work, like how to reduce their numbers. Like in the state estimation case, what I was trying is an unobservable system, but yet at least try to keep their neighbors observable, so that I can get some information from the neighbor, and through that neighbor I can actually estimate a state for the unobservable bus. But in that model also, if I don't have a measurement for the neighbor, then I'm gone. Like then I can't estimate it for the unobservable bus. So yeah, that trade-off is there.
Yeah, that's true. And my next question is that actually in distribution networks, we not only have the circuit breaker changes. Sometimes, for example, we have built some new households, and then they will have some new lines, and then we need to create a new substation. But all of this information might not be reported very in time. So in these cases, maybe state estimation has a task to detect such unreported changes. I'm not sure. Maybe in the future, I don't know if there is a possibility that through improving your proposed methods, then we can also detect this kind of topology changes.
Right. Yeah, actually, great suggestion. I would say, like I will think about it definitely. Yeah, that's like if an infrastructure is built, how could it be detected or not? Yeah.
It's not like in transmission networks, everything is very closely monitored. In distribution network, anything can happen, you know. Maybe some some households might feel the electricity, and we do not know.
Right. Yeah.
Okay. Thank you very much.
Thank you.
Just to mention, Joe Young, you see, again, we are returning back from topology estimation. You remember our discussions about topology estimation? Then you said, "Oh, Prof,
Actually,
I prefer not to do that."
Yeah, actually, recently one of my MSc students is doing some research on not specifically on topology estimation, but he is doing some research on how to distinguish different types of anomalies, like subnode change, bad data, and also fault, and that is changed on topology change. And maybe we can, when she finish her paper, maybe I can send to you, and you can input some of your suggestions, comments.
Yes, definitely.
Yeah.
Sure.
Great. Thank you, Jorian. So, is there anybody else who has risen its hands and would ask question?
Sorry. I have to go in a few minutes, so
we will be missing you.
Yeah. So I'll say goodbye first, and
okay, good. So yeah, thank you very much.
And see you soon.
Yes.
Yeah.
Bye-bye.
Thank you.
Yeah, I think Mustafa have some question to ask. Please, Mustafa.
Yes, hi. Yeah, thank you. And hello, Rajarshi. Thank you very much for your presentation.
Thank you.
At the beginning of your presentation, you mentioned that you assume the frequency remains constant.
Yeah. Right.
So, but like realistically, we have a variant frequency in the system. What would be the impact of considering variation in frequency on your modeling and estimation?
Right. So this is one assumptions that we made is a constant in frequency, because we are trying to capture the variation more on the voltage. So if the frequency changes, then as you said rightly, we have to include it as a state in the system. That's what I feel like, because the frequency then could become a state of the system. So maybe we can try to estimate that also along the way, because that will be changing. So maybe we have some measurements about that from a PMU, and we try to correct those. So yeah. So that has to be then included maybe as a state variable. Like that's what.
Right. So would there be any impact on the parameters you're estimating, right, such as voltage? Though voltage and frequency may not be very relevant, but there are research, I think also Vladimir is also doing the same thing, that there are some correlation between the voltage and frequency as well. Yeah. So if we consider when frequency is changing, probably some of your estates are also changing.
Right. So at that time, I think some information related to the frequency, like some equations relating frequency to power and frequency to other measurements, can be extracted and should be used. Like we need to think about that. Like that, I would say. Like one way I think is to include the frequency in the estimation process is by augmenting the state vector itself using frequency, so that we keep track of frequency as it evolves, maybe. But how to do that, like we need to think about, and it's a relevant question. Like as more DERs get integrated, the frequency variation would become pronounced. So yeah, that could be a way ahead. You are right.
Thank you.
And it is at least very important is not to make a mistake between 50 hertz and 60 hertz. At least this.
Yeah, right. Yes.
Great. Thank you very much.
Thank you.
And by the way,
yes, please.
Yeah, go ahead.
No, I wanted to say that actually in this type of estimators, frequency is normally not considered as something what could make a big impact. Frequency can vary plus minus. We have standards plus minus 0.5 hertz, and frequency could have impact to parameters. For example, omega L is X. That could be impact a little bit on parameters. it could maybe have an impact to load. But when it comes to load, okay, I'll ask the question later. But Mustafa, yes, you can ask further.
Right. Yeah. Thank you. And also, it was an iterative sequence of calculation in your model. So if you consider the delays that PMUs and RTUs taking time to send the data to your data center, and you're at the same time doing some iterative computations, would there be some impact of these delays on your accuracy?
Okay, so the thing that is to be taken care of is that the estimation should ideally complete between two measurement snapshots, like before two consecutive measurements arrive. In that time window, we should be able to calculate the states. That's why we called it a tracking estimator. But if that does not happen, then like we get delayed states, like they will queue up in the estimator before the estimator, and the estimator can only process it in a like sequence by sequence. So as a result, you will start observing delayed states, like if the iteration are not finished within the time frame between two measurements. Yeah, that's
right. Thank you.
Yeah, sure.
Mustafa?
Yes.
Further questions, please? The audience. So it's state estimation problem. It's application of estimators. Well, let me ask the question. When it comes to modeling, you mentioned that in your model, I'm now focused on modeling of loads, you use a constant power model.
Yes.
So I think we are aware that these are different types of models of load. Right. So if in your case, in the case of your network, the reality would be indeed constant power load, what means that whatever happens on the load connecting point from the perspective of voltage, from the perspective of frequency, your load would be constant power, P plus JQ. However, we are aware about, for example, different types of models. And also those who include even transient behavior of load, transient recovery model. So I actually recently, as editor-in-chief of a journal, checked a review of one of reviewers who really wanted to reject the paper and particularly accused the fact that active power, that the load model was constant power instead of other models. And then I was thinking, oh, it was maybe too harsh to insist on something like that and to reject the paper because of that. But would you give any comment on this about load model?
Yeah, actually, a load model, as you said, like it has impact on voltage stability and all, but from the perspective of a state estimator, I would say the load model, like if I assume, suppose a constant impedance load for a bus, but if I get data of as P and Q, so I can't update that impedance. I can only update the P and Q. So in that sense, like for state estimator, it is also quite sometimes dependent on the kind of data that we are gathering. Like we can choose a model of constant impedance, but then we need to know the impedance rather than the P or Q, or so how accurately we know the impedance is also another question that would arise. But with this constant power model, we can take the P and Q as the data, and we can go ahead with that.
No, but if the model is constant current or constant impedance, then actually P and Q would be different in these cases.
Yeah, P
so
and Q.
That's maybe just interesting. It's about, we are now talking about sensitivity analysis. What is the impact of the quality of load model? Or can we at all adjust the state estimator to a model in which load is behaving differently? So that's the first question. And then if it is the case, then to see what is the impact. But that's just an open question which could be just told.
Right. Actually, I saw some work related where they took constant impedance assumption on the load. And so in that case, what happened is that the load power itself became a function of voltage. So now you have a function of voltage on Y also.
Exactly.
So that was,
yes. These are voltage dependent models.
Yeah, voltage dependent.
I used to work on this topic from the perspective of characterizing demand. We would like to know what is P and Q. But P and Q are different for different types of loads. If you have more motors, then you have even transient behavior. If you have, interestingly, if you have inverter connected load, okay, maybe I can ask you, I'd like to ask you to challenge you. What do you think, how inverter connected load would behave?
How inverter connected load would behave. So that has to be decided mostly like power electronic interface loads. I see them behaving like constant PQ.
Exactly. I'll catch you. Exactly. That's it. So we did research on this topic, and the question was what is the model of inverter connected load and inverter connected power electronics connected load, and it behaved like constant power. That's good. Excellent. So very good. I personally think that it's a bit complicated question. So, but you could also guess. The likelihood that you will be right is 1 divided by 3. So maybe you made a guess, but I'm not. I think that you had your strong reasons behind it. But let me ask you one more question. I will not insist on many questions, but also jointly with Shandong University and the University of Manchester and Skoltech University, we worked on state estimator, which would be cyber attacks immune.
Okay.
What means, for example, to differentiate, this is what Joe Young just previously mentioned, but not to all details, how to differentiate different types of changes in the grid. For example, generation change, load change, but also attacks, cyber attacks, which could bring some changes. So have you came across some papers on this topic, or have you been thinking about it's how to detect cyber attack by using state estimator and then consider this data as bad data, for example?
I would say, like, I have not gone into much detail about that, but like some works I have read around that where so the problem of cyber attack detection is typically the method in which the attack is formulated, like what they are, how they are trying to fool the estimator. Like what I see is to attack a leverage point, to attack a critical measurement. So if they have some prior information about that, they can orchestrate the attack in a better way. But like I don't have much idea about cyber attack and how to detect them. That's enough. I can say like those are critical vulnerabilities.
Just think about that. This could be also one of research directions. By the way, today I'm going to Cyprus. I'm going to University of Cyprus, in which also Professor Saikat used to stay, and his host was Professor Elias Kyriakidis. And unfortunately, Professor Elias passed away 3 years ago, and on Monday will be day devoted to Professor Elias, and I was invited to give a VIP lecture. So that I'm now at the airport. Sorry for this background noise. I'm on my way to Cyprus, and this Friday seminar will be also mentioned in my presentation as a kind of remembering to those days when we worked hard together. And it was more than 10 years ago when also my former PhD degree student, Gustavo Valverde, who also worked on application of unscented Kalman filter for estimation of generator parameters, and jointly with Elias and Professor Jerry Haight from Arizona State, we published a joint paper. But with Professor Saikat, we published also with Elias, also Tiershubi from China. We published quite a popular paper in IEEE Power magazine. The title was "Measurements Get Together." What means we are now talking.
Yes, I read that article. Yeah,
I like this article. It was so nicely. Also, my former PhD student, who is now at Shandong, Tsai Deyu Tsai, was also one of the authors. Very nice memories.
Right.
So let me see if we have more questions from the audience. Can you please double check and ask in Chinese?
Okay, but I think there's no more questions, Professor.
All right, so it is Friday and it is already time for dinner in China, it looks.
Yes.
Am I right?
Yes,
I see. Oh, that's what we are now expecting to close this meeting. Also time for lunch, and honestly time for me to go to do boarding, because the boarding is about to start. But I really like this lecture today, and I would like now that all of us express our thanks to Raj for his brilliant presentation. And let me ask Raj, can you please update us? What have you published from your work?
So the state estimation work and topology estimation work that I published in power systems and smart grids, and parameter estimation I published in instrumentation and measurement. I had a paper from parameter estimation there.
This is fantastic. For these 3 IEEE papers.
Yeah.
This is fabulous. I must complain, you haven't sent anything to journal in which I'm editor-in-chief, but there is time. So we could think about a good special issue in which we will address these kind of problems, including topology estimation and cyber attacks. Very good. Okay, great idea. So lovely.
Thank you.
Phenomenal. We traditionally, before we close the meeting, we ask Weiyu to make a joint photograph. So Weiyu, please let us know what to do.
Okay, so if you have camera, please turn it on and I will take a joint photograph. Thank you.
So all participants are kindly invited to activate their cameras.
Yes, I will repeat it in Chinese, sorry.
Please.
请大家开一下摄像头。还有几位那个短期助理也开一下吧，谢谢。
Nice. Oh, also from India, very good, excellent. So nice to see all of you. Oh, lovely. Also from Holland. Very nice. What's the weather, Alexander, in Holland?
Actually, a bit better than usual. We have some sun actually today, so.
Oh.
Not as much as in Cyprus, I assume, but not as bad.
24 degrees waiting for me, but in Russia it was 6 degrees in the morning.
Oh.
How about Shandong? How about Jinan?
Oh, it's sunny, but a little bit cold.
All right, very good. Lovely. And Kanpur. How about Kanpur?
Yeah, Kanpur. I'm right now in my hometown actually. So here right now the weather is good actually, not that hot and humid. Kanpur, I think it is now better. I talked with some of my friends.
May I ask what's the temperature there?
Right now in my hometown the temperature is around 28, so it's good temperature. It's 28 degrees centigrade. It's good. It's usually it stays around 35, so 28 is good.
Okay.
Very good. Okay, so no snow. Okay.
Okay, now I'm taking the photo. Now, 3, 2, 1. Okay, I've taken the photo. Thank you very much.
Oh, excellent. So Ladies and gentlemen, thank you so much for this Friday seminar. Next Friday, we have another one, and this seminar will be also announced. Please let your friends know that we are doing this series, in my personal opinion, previous one.
Yeah, next Friday we will have Alexander from Technical University of Delft. Technology.
Yes, Alexander. Yes,
the correct name.
Alexander, what is the topic of your presentation? Please let us know.
Yes, so I will be talking about vulnerability of power systems, and particularly with the short-term voltage stability and system strength. So something that I'm working on currently, and some of our group here.
So reliability.
Vulnerability.
Vulnerability. Oh, good,
yeah.
good. Vulnerability, lovely. Oh, that's very good. Excellent. All right, excellent. Thank you very much to all of you, particularly to Raj Titu, who gave us a brilliant presentation. So goodbye, have a good evening, have a good day, and we stay in touch. Enjoy the weekend.
Sure. Thank you, Professor.
Goodbye.
Thank you, Professor.
Have a good weekend.
Thank you
Bye.
all.
Have
a good weekend.
Bye-bye.
Bye. Have a safe flight, Vladimir.
Thank you very much. All right.